we started discussing already one of the type of intermolecular forces, which is London dispersion forces. And these are non-permanent fleeting dipoles. And we illustrated with something like that, right? So chains of alkanes. Now here, the longer those compounds are, the larger, the more chances of interacting. So you expect higher boiling points, for example. But if you add branches to that and say, here you have 1, 2, 3, 4, 5, 6. But say that I have 1, 2, 3, 4, and 5, total the same molecular formula. This is C6H14. But now the branching out is not helping get this molecule close together to interact in the using their van der Waals forces. So now the more branching out there is, these interactions go weaker, makes harder. So you can draw another molecule with 6 carbon, let's say 1, 2, 3, and 4. That is even more branched out. You can also have this 1, 2, 3, 4, 5, 3, 4, 5, 6. More branching out. The more branched it is, they cannot get as close as that. So even though they have the same molecular formula, so they are constitutional isomers. So they share the same molecular formula, but they have different connectivity. Atoms are arranged in a different way. And the more branching there is, the weaker the forces. So lower boiling point. Again, remember, we're always thinking from liquid to gas. We need to break those forces to pull this molecule apart. So this will be having the same mass. The mass is no longer an effect. It was when I'm considering only this, say, not branched out alkanes. But as I branch out, these molecules will have the same formula, same mass, because of that. But as the branching is increasing, now I don't have that much of that. So weaker interaction between molecules. So I expect lower boiling point for that than for this. Now let's get to another type of intermolecular force. And now here I'll be talking about another important aspect. And here we're going to be looking at the geometry and if we have polar bonds or not. Dipole, dipole. I'm going to make a drawing of just a general dipole. Let's say that I have something like that, and I have a positive pole and a negative pole. We know by Coulomb's law that opposite charges will attract. So the type of interactions we'll be putting in the molecule, say this is a fluid, so negative close to positive, and this will continue on. And molecules, again, this is fluid, this is moving. And now I'm going to have maybe another here in a geometry. But this happens if I have a permanent dipole. So this will happen with molecules, say that I have CH3Cl, so chloromethane. So chloromethane, it is tetrahedral, but now I have one of the H's that was a methane replaced by a chlorine. So I have this. The geometry is tetrahedral, and I have only that one vector. It will not cancel out. So I do have a permanent dipole. It's different than 0. So now the molecule will have these characteristics, where the positive is on this end. So if I make, let me just draw like a little thing like that, like a shape. This end is my delta positive, the other end delta negative. So now the molecules can arrange this way. And so when you have the geometry in a permanent dipole like that, you have determined that using these two factors. Now I have this type of interaction, dipole-dipole. And that exists in many molecules so long that we have that a permanent dipole. Also, you have London dispersion forces, but this force is stronger. So ranking dipole-dipole is stronger than low non-dispersion force. Now I'm going to go into specific type, another type of intermolecular force, which we call hydrogen bonding. That's a special type of dipole, if you will. That happens when you have H's, you have hydrogens attached to either oxygen or attached to nitrogen. You can also say with fluorine, but other than hydrogen fluoride, we don't have other molecules to apply that. So let's look in the molecule if you have H's attached to oxygen or nitrogen. And let's draw a specific example. Now say that we have determined that the geometry of water is bent. Now this bond is very much polarized. This is your delta positive in. This is also delta positive, delta negative. So now the molecules will interact with another molecule that's positive in with the negative of another molecule, like that. And we say this is similar to the dipole-dipole interaction, but it's much stronger. The difference in electronegativity is big. So now, this happens in water, but this also could be interacting with another. So we're going to have like a network of hydrogen bond interaction. That is strong interactions. And again, if you're thinking the liquid and you want to go into the gas phase, now you need to supply energy, supply heat to increase the kinetic energy of the molecules and break those interactions. These explain why the boiling point is such a small molecule as water and a small mass. Remember that here you can do the molar mass by adding the atomic masses. And you have H2O. So you will have the mass of the oxygen and the mass of the nitrogen. You add that up. But point is, it's very small. But because it has those interactions that are very strong, the boiling point is quite high. We know by our experience in the lab that the boiling, I'm going to do BP, is at 1 atmosphere is 100 Celsius. So pretty high for such a small molecule. Now we have other examples of hydrogen bonding. If we consider, say, ammonia, that, again, what is the characteristic? That we have a hydrogen either attached to oxygen or nitrogen. So I can also have here a network of hydrogen bond. That is going on and on. So in that, again, you need to break those interactions to put the molecules from the liquid to the gas phase. And supplying that energy implies that you're increasing the temperature. That temperature, remember, is a measure of kinetic energy. So that's what we're doing. These are the three types of interactions that we'll be analyzing when we go to organic molecules to rank them according to boiling point. And we'll also be talking about solubility using the type of interaction between molecules.